In the last video, we solved this particular problem of a man running to catch a bus. Initially, the man was 40 meters from the back end of this bus where the door is. He's moving with constant speed. The bus starts from rest at this instant at t equals 0, its speed is 0, but it's accelerating to the right. We found that after 20 seconds, the man just catches the bus, and that word just was important, as I explained before. So the man needs to hop on the bus at the instant he catches the bus, because if he doesn't, the bus will keep moving ahead of the man, because the bus is accelerating, whereas the man is moving with constant speed. The man's speed doesn't change, his acceleration is 0. So we solved that problem. We found that the man's speed would have to be 4 meters per second. The bus's acceleration would have to be 0.2 meters per second squared in order for the man to just reach the bus and get on the bus. Now what I want to do in this video is just discuss a little bit more about the distance time graphs involved. So in the previous video we put SM equal to SB, where SM is the distance of the man from the origin and SB is the distance of the bus from the origin. So let's look at SB first. We saw that SB is 40 plus the familiar formula, UT plus a half AT squared applied to the bus. We have to add on the 40 because at t equals 0, the position of the bus from the origin is 40. If we put 0 in for t, these terms will go out. We have to get 40, not 0. UB for the bus was 0, so this term goes out. And the acceleration of the bus AB, I'm just going to leave as AB for now. So I'm going to write it as 40 plus a half ABT squared. So for different values of AB, we're going to get different distance time graphs. What I will do is consider this particular value for AB. AB equals 0.2. If AB is 0.2, a half of AB is 0.1. So I can then go and graph this. We see that when t is 0, s is 40. So here's a distance time graph, s against t, not v against t, but s against t. When t is 0, s is 40. And this is quadratic in t, and the coefficient here is positive, which means it's going to look like this actually. Actually, it's going to increase. When t is positive, s is going to be positive. You see what's happening? As t increases, then this thing is going to increase. So it's going to look like this. Look at the case for the position of the man. SM is UMT plus a half AMT squared. He starts from 0, so we don't have to add anything on here. His acceleration is 0, so this term goes out. So we just have his speed times time, UM times T. And we found that when UM is equal to 4, that he will just catch the bus. So let's look at his graph. Well, it's just linear. It just has the same form as y equals mx, where m is the slope. Slope here is 4, positive slope, so the line looks like this. It starts at 0. When t is 0, s is 0, as we have here. For the man just to catch the bus, we see we'll only get one solution, one point where this line crosses the curve. It's possible to get more than one solution. If the man caught up with the bus, we could have something like this. If we change the value of AB, if we change this value here, if we increase it actually, well, actually not increase it, but decrease it. If we decrease the acceleration of the bus, then the man could reach the bus at 2 different times. He could reach the bus firstly here for some value of t, whatever this time is. This is the first time he reaches the bus. And if he didn't hop on the bus, if he just kept going, he would overtake the bus. That's where the green graph is greater than the blue graph. And he'd overtake the bus, but only temporarily, because the bus is accelerating, whereas he's moving at constant speed. So the bus would catch up with him at this time. So you'd see that there would be 2 times when the man coincides with the bus. But that's not what we're interested in. We were interested in the situation where he just catches the bus, and that means we only want one solution here. Now, we could also notice the speeds of both man and bus at this particular time. This time is 20. What is the speed? Well, we could use the speed formulas, or we could just do differentiation. The speed is ds dt. So v equals ds dt. That's the speed of either bus or man. So the speed at t equals 20 is the derivative, which is actually just the slope of the tangent at this point. So the speed for the man is the slope of the tangent to the graph for the man, which is 4. The slope is just this number. So dsm dt equals 4. But that's just equal to dsb dt, which is also 4, because the tangent to the graph of SB has a slope of 4 as well. It's just this line here. So the tangent to the line is the same as the line. Tangent to a line is just the line itself. That slope of that tangent is the same as the slope of the line. But the slope of the tangent to the graph at this point is also the slope of this line. So you can see that this here is Vm. Speed of the man equals the speed of the bus, Vb. In the second part of the question, where we're given that the man does not actually catch the bus, if you remember that in the second part of the last video. So in that situation, we found a time for when the distance between SB minus SM is a minimum. And we found that minimum distance to be 17.5 meters. So I won't go through all that again, but we could see it from graphs if we were to draw out the graphs for the situation in part 2, which I won't go into in detail, but this would be the minimum distance, SB minus SM. And I can't remember the time, I'll just look it up. Actually, this occurs when his speed is 3, when the speed of the man is 3. So we need to alter, well, just this formula here. SM was 4t previously, now it's going to be 3t. His speed is, his distance is u times t plus a half a t squared. His acceleration is 0. So we just get this. And this is the minimum distance, 17.5 meters. It occurs at t equals 15 seconds.